Hello, in this video we're going to talk about linearization, and before we do this for multivariable functions, I'd like to recall some of our results from Calculus 1. So recall from Calculus 1 that when you've got a function f that's differentiable in a neighborhood of a, you can find the linearization of f as follows. F of x is approximately f of a plus f prime of a times x minus a. So first of all, where is this coming from? Well, recall up above that we had the equation of a tangent line, x naught, y naught, and that result from our previous video looked like y minus y naught equals f prime of x naught times x minus x naught. Well, if you move over this y naught term, so you move that to the other side, what do you get? You get y equals y naught plus f prime x naught times x minus x naught. So what we're going to do is we're just going to replace the x naught with a. And so what we get here, we get f of x equals f of a plus f prime of a times x minus a. And that's our linearization. Okay, so this is the equation of a tangent line, and that's going to be a pretty good approximation for the function in a neighborhood of a. So if we take a look, for example, at our function for sine of x, so recall that sine of x has domain all real numbers, and the range goes from -1 to 1. Okay, so let's find the linearization of f of x at a equals 0. Okay, so there's our a equals 0 right there at the origin. We want to find a linear function that does a pretty decent job of approximating sine of x near x equals 0 or a equals 0. So there's our linearization formula, and so what we have here is we have that sine of x is approximately, let's see, f of a, well, sine of 0 plus the derivative, which is cosine evaluated at 0 times x. In other words, in the neighborhood of 0, we have sine of x is approximately x. And so you can imagine if you're working on a really complicated problem in engineering that's got a bunch of sine terms and you're working close to the origin, you could replace them by x, and that would really simplify your calculations quite a bit. Okay, so I've drawn in what the function y equals x look like. So this is our linearization. It does a really good job of approximating sine values when we're close to 0, and the farther we move away from 0, the worse our approximation does, but it's really good when we're close to 0. Okay, so now let's turn our attention to the linearization for multivariable functions. Suppose f is a function of x and y. Also suppose that f is differentiable in a neighborhood around AB. So AB is some point in the xy plane. F is a lumpy bumpy function that sits above or maybe below the xy plane, and it's differentiable, so it's nice and smooth. Got a nice smooth surface. Okay, so the linearization of f near the point AB is given by the following. It's basically the equation of our tangent plane with that one term moved over to the other side. So here it is. We can say f of xy is approximated by f of ab plus the partial derivative of f with respect to x evaluated at ab times x minus a plus the partial derivative with respect to y evaluated at ab times y minus b. Okay, so let's do an example. Let's find the linearization of f of xy equals x times e to the xy near the point 1, 0, and we'll use the linearization to approximate the value of f of 1.1 comma negative 0.1. So first thing we need to do here is we need to find our partial derivative. So we'll find the partial derivative of f with respect to x. And once we've figured that out, we will evaluate that at the point 1, 0. Similarly, we'll need to figure out the partial derivative with respect to y. Okay, so the partial derivative with respect to x. Remember that x is our variable here, and so we'll need to use product rule for the derivative. So the derivative of the first term, which is x, derivative there is just 1 times the regular second, plus the derivative of the second term is e to the xy times y times our first term. Evaluating that at 0, 1, evaluating that at 1, 0, we get e to the 0 plus 0, and that just equals 1. Okay, so we'll use that value in a minute. Next, let's find the partial derivative with respect to y. In this case, y is our variable. Everybody else acts like a constant, and here we get x squared e to the xy. Evaluating that at 1, 0, we get 1 squared times e to the 0, and that turns out to be 1. And we'll use that result in a minute. Our formula for the linearization looks like f of xy equals f of 1, 0 plus the partial derivative with respect to x evaluated at 1, 0 times x minus 1 plus the partial derivative with respect to y evaluated at 1, 0 times y minus 0. And this should be an approximation. F of xy equals, f of xy is approximately, let's evaluate f of 1, 0. Evaluating that, we get 1 plus our partial derivative with respect to x evaluated at 1, 0. We have already computed that. That turned out to be 1 plus the partial derivative with respect to y evaluated at 1, 0. We already computed that result, which was 1. So cleaning this up, we say that f of xy is approximately 1 plus x minus 1 plus y. And we get some things that cancel, so final result, x plus y. So let's use this to approximate the value of f of 1.1, comma, negative 0.1. So if we wanted to approximate this value without the use of a calculator, well, that would be approximately 1.1 is going in for x, and a negative 0.1 goes in for y, and that turns out to be 1. And the true value, if you do get out your favorite mathematical software like Mathematica, the true value is somewhere around 0.98542, whatever. But the point is, our approximation did very, very well.